Hello everyone, welcome to Mechanics of Fluids tutorials. So in this video we are going to discuss about the loss of energy due to contraction in pipe. Okay, contraction means there is a reduction in the cross-sectional area of the pipe. So when you take a pipe of larger diameter and that is connected to smaller diameter pipe. So this case you can consider sudden contraction in the area of the pipe. So due to this sudden contraction, again the variation in the velocity takes place, which causes the loss of energy. Okay, so which is again minor loss. Assume here the flow of the liquid is taking place with certain velocity through this pipe. So when it reaches the smaller diameter pipe, again there is a sudden abrupt change in the cross section area, which that cannot be handled by the flow of the liquid. So in the form of the jet, it will try to come into the smaller diameter pipe. So in that case, the separation of the liquid again takes place from the solid boundary of the pipe, and again it will reach the cross section area of the pipe slowly with varying velocity. Okay, again the flow cross sectional area becomes equal to the cross sectional area of the pipe. Like this the flow pattern takes place for the reduction in the cross sectional area, that is the contraction in a pipe. Okay, so because of this again the velocity variation is taking place, which is causing the loss of energy. So I want to give an expression for the loss of energy due to the contraction. So for that I want to assume section 1 here, and I want to assume section 2 here, and at the Vino contractor means where the minimum cross sectional area is taking place for the flow of the liquid here. So minimum cross sectional area takes place here for the flow of the liquid where it is separated from the solid boundary of the pipe. So I want to assume this section as C. So at section 1 it can maintain the pressure P1 and velocity V1 and area A1 we can assume, and here at section 2 it can maintain pressure P2, velocity V2 and the area A2 it can maintain, we can write it as, and at the C also it can maintain certain area AC, which is the smallest area is taking place for the flow of the liquid, and at that place again it can maintain separate velocity, which is we are assuming VC. So by these assumptions we can derive an expression for the loss of energy due to contraction in pipe. And here again, while finding this we have to observe the flow pattern variation. So how the flow pattern variation is taking place means here slowly the cross sectional area is decreasing and increasing. Okay, so decreasing and increasing again here, that means we can consider that whatever the loss of energy taking place due to the cross sectional area variation, that is the contraction in pipe, that can be equal to the loss of energy due to the enlargement in the cross sectional area. Why? Because decreasing and increasing in the cross sectional area for the flow of the liquid is taking place. So due to this only we are facing the loss of energy. So that means because of the minor losses we can say that whatever the loss of energy is taking place through the contraction in pipe, that can be equal to the loss of energy due to the enlargement in the cross sectional area of the flow of the liquid. So that means here we can write it as loss of energy due to loss of energy due to contraction. Okay, loss of energy due to contraction can be written as again loss of energy due to enlargement in the cross-sectional area of the flow from C to 2. Okay, so the loss of energy due to contraction I want to assume it as HC. Okay, so the loss of energy due to enlargement, already we have discussed about the expression for this loss of energy due to enlargement as v1 minus v2 whole square by 2g for the two sections. Similarly here we need to apply that formula to section C and section 2. So when you apply the loss of energy due to contraction, we can obtain vc minus v2 whole square by 2g. Okay, this is the equation we can obtain for the loss of energy due to contraction, but still it is not sufficient, it is not exact formula for finding loss of energy due to the contraction. Why? Because it is impossible to find out the velocity at the Vino contractor VC. So we need to modify the equation until we get the equation in the form of velocity at section 2 only, that is the velocity in the smaller diameter pipe. So for that I want to take in HC equation v2 square as common. Okay, I want to take V2 square as common, that is V2 I am taking from the bracket. So we'll be getting Vc by V2 minus 1 whole square. Okay, so assume this equation as 1. Next I want to take the continuity equation. Okay, so what is continuity equation? The continuity equation states the flow rate is constant at any point. So the flow rate at section 1 should be equal to at section 2. Similarly, flow rate at section C should be equal to flow rate at section 2. So I want to apply this continuity equation for section C to section 2. So for that we'll be getting AC Vc is equal to A2 V2, because the flow rate formula is area into velocity. So the AC Vc is equal to A2 V2 will be getting. So now I want to write Vc by V2 is equal to as A2 by AC. Okay, this is the form we got for Vc by V2, which is reflecting in the first equation. So again we have one more term, which is coefficient of contraction. Okay, just like a coefficient of discharge, we are having one more dimensionless quantity, which is coefficient of contraction, which is represented by Cc. So the coefficient of contraction is defined as the area at the vena contracta, ratio of area at the vena contracta to the area of the flow, that is area of the pipe here. So we can write it as area at the vena contracta is AC and area of the pipe is A2. Okay, so when you keenly observe the above equation, so this Vc by V2 is equal to A2 by AC. So for getting AC by A2 in this place, how can we write it as Vc by V2 is equal to 1 by AC by A2, we can write it as. So in place of this AC by A2 we can write C is the coefficient of contraction. So now again we can write it as Vc by V2 is equal to 1 by Cc. Assume this equation as, second equation. So now substitute second equation in 1. Okay, so Hc is equal to V2 square by 2g into Vc by V2 means we can write it as 1 by Cc minus 1 whole square. Okay, this is the equation which is used for finding the loss of energy due to the contraction in pipe, and there is a standard value for Cc which is given as 0.62. Okay, the standard value of Cc is 0.62. Okay, so when you substitute that 0.62 in the equation, we'll be getting the Hc formula as Hc is equal to 0.375 into V2 square by 2g. Okay, this equation also directly we can use if rather than considering this equation, because of Cc standard value is 0.62. And similarly, if in the problem the Cc is not given, if the Cc value is not given, then we have to consider the formula as Hc is equal to 0.5 V2 square by 2g. Okay, so this is the formula again. If in the problem the Cc value is not mentioned, if the Cc value is mentioned as the 0.62, directly we can take this formula, which is 0.375 V2 square by 2g. If the Cc value is not given, then we have to take 0.5 V2 square by 2g. Okay, this is the simplest form of the derivation for the loss of energy due to the contraction in the pipe, by simply applying the loss of energy due to the enlargement for the flow pattern is taking place for the flow of the liquid in this pipe. Okay, like this the flow pattern takes place, again the enlargement is taking place. Due to that, we can say that loss of energy due to contraction is equal to loss of energy due to enlargement from C to 2. Okay, so by applying this simple knowledge, we can derive the equation as Hc is equal to V2 square by 2g into 1 by Cc minus 1 whole square. Okay, so the units are meters only, meters of water. So I hope you understand how to derive an equation for finding the loss of energy due to contraction. And please subscribe to my channel, and please share my videos with your friends. And if you have still not subscribed to my channel, please subscribe to my channel. Please encourage my channel. And once again, thanks for watching my video. Thank you all.